Okay, welcome to the 18th class meeting. And today we are going to cover some PDF files I uploaded during the weekend. So you go to the homepage of the lab and go to the teaching, and then you have in cyclostationarity and signal processing and communications. If you go to the schedule download, you will see this year's spectrally correlated random processes handouts, where here for today's class meeting 18, I've uploaded several PDF files. I believe you have more confusion than clarification in some concepts, so I've decided to cover these topics. So please download all the PDF files and let's proceed. So these PDF files are, as I wrote here, co-authored by Gemini AI and myself. And even though I say Gemini AI, but most of the organization and contents and correctness are all on me. So I have the credit and also have the responsibility. So if I find something wrong, I will update these files. So please check whether you have this November 6th date or not. If you see some different dates, then probably I've updated, possibly corrected some typos generated by Gemini or myself. Got it? So the first PDF has title, second order random processes, definitions, implications, and significance. One of the reasons why I've decided to talk about this topic is that even though I said many times second order random process, finite power random process, but I remember I didn't tell you why this is so important. So let me tell you. So here, as I've already told you many times, the definition is very simple. You have of course, I'm just talking all about continuous time random processes, but most of the concepts can be straightforwardly extended to discrete time random processes. So you can do it yourself, and those extensions may directly appear on your next take-home exam, probably taken next weekend. I'm not sure this weekend or next weekend. So here goes a continuous time random process x of t. And you have, we assume x of t is complex valued. Of course, it can be real valued. So you take the magnitude square and take the ensemble average. So at each time t, the magnitude square of x of t becomes a random variable, and you compute the expectation of that random variable. Or you may view it as ensemble averaged instantaneous power of x of t. And we assume that this value is finite. By the way, when you have something like this, most of the times it means this value exists actually. So this is about the existence of the power. Got it? Of course, since this is the magnitude square, the expectation must be non-negative. Anyway, so for all t, and here, this index set or domain is denoted by I. It could be a time interval, finite time interval 0 to, say, 0 to capital T, or it could be the entire real line. It doesn't matter. Anyway, the formal definition is this, very simple. And let's see the implication. And implication is related to the Schwarz inequality. So last time when we talked about the mean square periodic random process, we've seen some flavor of Schwarz inequality in computing moments. And that was very useful to show that the mean square periodic random process has, which means there exists a periodic mean path. And also you've seen that the autocorrelation function is not only periodic in T, but also periodic in S. And you can choose any multiple of capital T for T and any integer multiple of capital T for the parameter S, something like that. And here, the implication from the Schwarz inequality says that the mean path or mean function exists for all T. So this second orderedness implies mean path exists, and also the variance also finite, means exists for all T. Got it? So let's see why this is so. And the idea is not that difficult. Just a second. Where is that one? I will put some. Just a second. This one. Oh, okay. So I pasted this repeating use of Schwarz inequality here. By the way, so in the last class meeting, I talked about this inequality and said that it could be proved using Jensen's inequality. And it can be also proved using Schwarz inequality. Let's see that first. So first thing is this one. Suppose you have a convex function phi, then what do you have? You have Jensen's inequality saying that expectation of function of a random variable upper bounds function of the expectation of the random variable. So if you switch the order of function phi and expectation operator, then you have an inequality. And this inequality is guaranteed as far as phi is a convex function. So the proof of this one is not that difficult. You can prove yourself if you want. But the key is that not only Jensen's inequality, you can use Schwarz inequality. By the way, here, what we use is that the function phi of x equals absolute value squared or magnitude squared function. Then for real x, this x squared is same as x squared, so you have convexity. And due to this, you have this inequality. Got it? Another one is that, another simple one is using the non-negativity of variance. And we know that when you have a random variable, generally complex valued, then what you have? Variance of x is actually, by the way, this is for real. For complex, you have variance of x equals expectation of x squared minus expectation of x squared. So since this is non-negative, you have the inequality. Got it? The last one is using the Schwarz inequality. So here we have a general form of Schwarz inequality for real random variables. So if we have complex, then we have xy conjugate magnitude squared is less than expectation of x magnitude squared times expectation of y magnitude squared. And here the trick is that you set y equals 1. So here very special case. Then what do you have? Here you have y equals 1 means expectation of x magnitude squared is less than expectation of x squared. And this becomes 1. Got it? So you have the proof of this inequality in 3 different ways. And I talk about this third method, which is used again for our proof of the existence of the mean and variance. So here, as we've done in the periodic mean square periodic random process, we can do the same thing. So what do? We have, this is finite for all t. Then what do we have? We have just the inequality. Right? We've just seen this inequality. What does that mean? The leftmost side is upper bounded by infinity for all t, which means that this one exists, and of course finite for all t. What does that mean? Expectation of x of t exists and finite for all t. So we have the mean process well defined. Got it? So the first consequence is this one. And what about the second consequence? And our definition of variance at each time is simply what? This one. And we can show that, what is this one? This is x of t squared minus, if I remember correctly, this one. Got it? If you expand, you will have this one. So we've just seen that this is finite, which means exists. And we've just seen that is also finite, exists. So its subtraction is finite and exists. Got it? That is actually shown here. But what about more than just the instantaneous variance of random process? So we will consider autocorrelation function. So for the autocorrelation function, what can you say? Can you show that the autocorrelation function exists for all T1 and T2 if random process is a second order random process? Can you do that? So here goes the proof. So we start from the Schwarz inequality for complex valued random variables u and v. So we have u times v conjugate and take the expectation, which can be a complex number. So we take the norm squared or absolute value squared or magnitude squared. And then we have what? The second order non-central moments product. Now, what we do is that at t equals t1, x of t1 is a random variable u, and at t equals t2, x of t2 is a random variable v. So we plug in these two here in equation 7 to have at the leftmost side the autocorrelation function magnitude squared. And here we have what? The second order non-central moment of x of t1 and second order non-central moment of x of t2. By the way, the first factor is finite by definition of the second order random process. And second factor is also finite. What does that mean? Finite times finite is finite, which means that this exists for all pair of t1 and t2, right? So what do we have? Some magnitude squared value exists. Right? So that's why we have autocorrelation functions existence. And similarly, autocovariance functions existence can be easily shown from the existence of autocorrelation function because autocovariance function can be written this way. Got it? By the way, I haven't proved whether complementary autocorrelation and complementary autocovariance functions exist or not. And That's up to you. Got it? So under the assumption of the existence of the magnitude square expectation of magnitude square of x of t, the question is, can we show the complementary autocorrelation and autocovariance function exists? Got it? Anyway, so we are done. And by the way, significance of this second orderedness or finite power, ensemble averaged instantaneous finite power over random process is very important in the theory of Wise-and stationary random processes, because the definition of Wise-and stationarity relies on the existence of mean path and the existence of autocorrelation function when we expand our theory, because it is the first and second condition for the definition of a Wise-and stationary random process. Got it? And also, for the Wise-and stationary random process, since the autocorrelation function exists, then we can define the power spectral density if the index set, the domain of the random process is the entire real line. Got it? Anyway, so now you see why this second orderedness over random process is so important. By the way, I haven't written here in this PDF, but let me clarify some other related definitions. For complex valued random process, so this is the definition of conventional Wise-and stationarity of a random process x of t. Of course, here we assume that the second order random process x of t is Wise-and stationary. What about we include not only the mean path, but also the autocorrelation function and complementary autocorrelation function? By the way, this function, these two functions are different from these two functions because the left functions are two variable functions and the right functions are single variable functions. So we use the same name for different functions with different domains. Anyway, and this random process is not by me, is named as second order stationary random process. And I do not completely agree, but anyway, WSS, SOS, so second order stationary. It's not stationary up to the second order. It's not, okay? Be careful. If you remember the textbooks, a random process is stationary, to order 2 is what? You have the CDF of the random process equals what? Equals the CDF of its origin translated version for all t, for all delta, and for all, of course, x, because CDFs are the same. And we have what? The second order CDF, which is the joint CDF of two random variables. Are the same. Just a second. Yeah. Something like this. So be careful. So it's very confusing. Second order stationarity is different from stationarity to order 2. Got it? So if you just say second order stationary, many people who are not familiar with this concept, this definition, will think about that one. So whenever you talk about second order stationarity, remind that it's different from stationarity to order 2. Now, similar to the Y-sense stationarity, we may have what? Y-sense cyclostationarity. So here goes the copy and paste of that one. Okay. Okay, good. So a second order random process is Y-sense cyclostationary with cycle period t if what? The mean path is periodic for all t, and autocorrelation function is what? Periodic in t1 minus t2 with period t. Got it? And now, similar to this definition of second order stationarity, we may introduce the definition of second order cyclostationarity with cycle period t if, of course, the mean path is periodic with period t and autocorrelation function is periodic with period t in t1 minus t2, and its complementary autocorrelation is periodic with period t in t1 minus t2. Got it? By the way, I defined this one just following the definition of second order stationarity. If we accept this definition, then it's natural to define second order cyclostationarity in this way. There is no other way. So, got it? Anyway, be careful. Let me emphasize again. Second order stationary random process is not a well-known definition because many researchers, even though they handle complex valued random processes, 99% of them ignore the complementary autocorrelation or autocovariance. So they just define Y-sense stationarity and Y-sense cyclostationarity in terms only of mean path and autocorrelation function. So whenever we want to define in terms of complementary autocorrelation function and also, complementary autocorrelation function, then we need something more. Got it? Like this. So I believe now I clarified more than I confused you. Now, this is a very interesting question about the origin of Fourier transform with respect to delay in spectral analysis. For example, as I just have told you, when you have a Wise-and stationary random process, in order to find the power spectral density, what do? The Wiener-Khinchin theorem says that you first find the autocorrelation function of the second order random process, which is a function only of the time difference T1 minus T2. I will define the time difference as tau as T1 minus T2, the first parameter and second parameter associated with the conjugation of the random process. And when I was an undergraduate student, and even when I become a graduate student, and even when I become a professor, I wondered why this Fourier transform with respect to delay tau gives us the power spectral density. So let me ask you, why? What is the origin of this Fourier transform with respect to some strange notion of delay? So today, I'm going to do my best to clarify this one. So let's start. We start from the definition of energy spectral density over deterministic signal. Of course, we assume kind of second ordered signal. What does that mean? We assume that the signal x of t is a finite energy signal. So let's start from the energy of the signal. And here, even though I said E, just you may say EXX, okay? The reason why we put double X is that sometimes you can define cross energy by extending this definition. So let's define the energy of a deterministic signal, complex valued, as this one. Then we may define the cross energy as what? X of t times y conjugate of t dt. Got it? No problem. And this is kind of interesting in that you have energy of the summation of two signals, x and y. Then what do you have? As you already know, you have energy of x and real part 2 times the real part of EXY and energy of y, right? If you expand, then you have two cross terms. They are conjugate pairs. And so you have 2 times the real part of the cross energy between x and y. Got it? So in general, you have the cross term. That's why it's convenient to define the cross energy and rewrite the energy of a sum of the signals in this way. By the way, you need to pay much attention to the fact that the energy is always non-negative, because the integrand is magnitude squared, right? So integrand is non-negative for all t. So if it exists under the assumption of finite energy, it must be a non-negative number. The problem is that the cross energy is not a real number in general, right? It's a complex valued signal. So cross energy is a little bit misleading because we believe energy is non-negative unless we want to talk about the change of the energy, something like that. Got it? So be careful about these two facts. Got it? Now, from the Parseval's relation, you already know this energy of X can be written in which way? In this way, right? So Parseval's relation says that your energy of the signal X of finite energy can be computed by integrating the instantaneous power of the signal for all t, or you may integrate the magnitude square of its Fourier Plancherel transform actually for all f. And you've seen many textbooks call this integrand in the Parseval's relation as what? The energy spectrum or spectral density of the finite energy x of t. And one of the reasons is that if you integrate this function, you obtain the energy. And it's a function of frequency, so it's very appealing to call it energy spectral density. And interpreting it as what? The contribution of the signal energy at specific frequency f. However, this claim is very dangerous because you've not proved this fact. So here goes x of t, and you have a very narrow bandpass filter at f equals f0 with width epsilon, and you have the output signal y. And let me ask you, what is the energy of the output y in this case? So you have x of t, you have a bandpass filter with height 1 and width epsilon. And the output is defined at y of t. And the energy of y, if its Fourier transform is well defined and smooth enough at f0, what do you have? You have this value for the energy. Why? From the convolution theorem, you have output Fourier transform equals what? Input Fourier transform times the transfer function, which is defined as what? Sorry about that. Fourier transform of the impulse response. So if you take the norm square, then you have norm square, right? And then if you integrate this energy to obtain the energy of y, then what do you have? Since this is a very narrow bandpass filter, you have x of f0 magnitude square times epsilon. Got it? So as you see that the output energy is that one. What does that mean? Now we can physically interpret this magnitude square of x of f as what? The energy portion in x of t at f0, right? The reason why I emphasize this one is that sometimes we just accept that if you integrate some function of frequency and get some physical quantity, we want to interpret that one as this one's density. Sometimes it's very dangerous without checking this type of result. Anyway, happily, this energy spectral density really means energy of x of t at f. So we are happy so far. Got it? So this energy spectral density is well defined and well named. Got it? Now, here goes the trick that is rarely written in most of the undergraduate level textbooks. So let's see. this one can be written as the product of x of f times x conjugate of f. And what is each one? Each one is the Fourier transform. So we can easily see that the energy spectral density is what? Fourier transform of x of t magnitude squared. And here goes the interesting part showing this one. So let's consider the inverse Fourier transform of this one, energy spectral density. Because this is a frequency function. So let's take the inverse transform. Then what do we have? That is what? Just the inverse Fourier transform of, so let me write it here. Inverse Fourier transform of x of f times x conjugate of f. Now, from the multiplication property of Fourier transform or convolution property in time domain, we have what? Convolution of the inverse transform of x of f and inverse transform of x conjugate of f. So what do we have? We have x of t convolved with x of negative t conjugate. Got it? So we have kind of convolution of x of t and its time reversed complex conjugate. Got it? This is so obvious, and probably up to this line you've seen in some exercises, or it's too obvious fact in signal-gen systems. But now we rewrite this convolution using the definition of the convolution integral. Then here comes the interesting part. So here for the integration variable, the Gemini used variable lambda. So as you see that if you choose integration parameter lambda for the first one, then for the second one, what do you do? In convolution, you flip and delay by lambda. So here, you flip and delay by t, since this is the parameter. And you integrate with respect to lambda. So here, t minus lambda is already time flipped in the lambda domain. Got it? So this is not that difficult to have that one. So eventually you have what in lambda domain? You have function of lambda and function of lambda conjugate delayed by t. So far, no problem. Now, let's compare this one and that one. Okay. Just a second. Equation 2. Yeah. By the way, let's see the let's define this time average autocorrelation function over deterministic signal first. So let's define time averaged or time average autocorrelation function over deterministic signal x with the parameter tau as what? We have x of t plus tau times x of t conjugate integrate over for all t. Then you have a function parameterized by tau. And by the change of variable, you can also use integration parameter t for the first vector and t minus tau for the second vector. And similarly, you can use t plus tau over 2 and t minus tau over 2 for the first and second argument of the functions. As far as the left argument minus right argument equals tau, actually you have uncountably infinite choice of these two arguments. And here, interesting part is that one. So let's compare this one with we've just seen here. What is that? It's simply Rxxt, right? Compare these two. If you change t to lambda first and tau to t, then you have the same thing. So these parameters t, lambda, tau confuses you a lot, but after you sort them out, reminding yourself of the fact that any parameter can be used for integration variable as far as it is not doubly, triply used. So you eventually have what? The inverse Fourier transform of the energy spectral density is actually the autocorrelation function parameterized by t, or if you want, it's same as autocorrelation function parameterized by tau, as far as when you Fourier transform, you pair tau and f. Right? Usually we pair tau and t for the inverse and Fourier transform and inverse transform. But as far as you use tau, then you have this result. So eventually we have what? This interesting result. Energy spectral density is the autocorrelation function as a function of tau, Fourier transformed with respect to tau using the variable f. Right? So what does this mean? Energy spectrum of a deterministic signal requires you to what? To perform Fourier transform of the time averaged autocorrelation function as a function of tau, right? With paired parameter f with tau. Got it? So this is the origin of your power spectral density, for example, has the Fourier transform with respect to tau with the paired parameter f. And we are going to see it in the next slide. So do you now have the idea about this origin of the Fourier transform with respect to delay to compute the energy spectrum or some power spectrum? Got it? So naturally, you need delay parameter tau. And your delay parameter may appear in this form of the delay. So actually, this is advance, this is the delay, and this is kind of symmetrical advancement and delay that do not matter when you compute the autocorrelation function. Because we assumed that x of t is finite energy signal, translation of the origin doesn't change the energy of the signal. So we have this result. Got it? Now let's see the power spectral density over general non-stationary processes. And then we specialize this result for Wise-and stationary random process. And this derivation actually can be found from that KMOOC lecture I uploaded in the YouTube of my channel, and also on the class, the lab homepage of the classes section. Anyway, so unlike many textbooks, the power spectral density of a second-order random process is defined first by truncating the random process in the time domain, or multiplying a rectangular window to the random process. So we have truncated version of x of t, time truncation. So x sub capital T of t equals x of t for all t from negative capital T to positive capital T and 0. And now, we can perform Fourier transform on it. By the way, some of you got some points lost in the first take-home exam by simply computing the Fourier transform of the random process. This, in general, does not exist for every sample path. So you can't do this, even if x of t is a second-order random process. You can't do that, okay? However, you can do that for a truncated version. Got it? So now we may define the Fourier transform of truncated version of x of t. So what do? We compute the energy spectral density first by taking the magnitude square of it. So here, this one is what? Magnitude squared. Got it? So this serves as a kind of energy spectral density of the truncated version of f. Sorry about Fourier transform squared. Not this yet. Got it? Since we want to increase this length 2t to infinity, we have what? We have a problem. Because since we assume that the random process is of finite power, in some cases, not every cases, if you compute the energy of each sample path, it could be infinity. So if you want to define the power spectral density of a random process who has finite power sample path in most of the cases, then this definition is very useful. By the way, be careful. Sometimes your random process is only defined on a finite interval. In that case, even if it's a second-order random process, you don't need to define power spectral density. You may define energy spectral density just given that interval. Be careful. Okay? Anyway, so you take the ensemble average of the energy spectrum, and then you take the limit as t tends to infinity. However, you divide it by the length of t so that you have the unit of power for this right-hand side. And if this right-hand side exists, then it's called the power spectral density of a random process, whether it's stationary, Y's and stationary or not. Got it? So this is the definition of power spectrum. And from this definition, you can easily see what happens when you delay the random process to the power, when you take the conjugation of the random process, when you scale something like that. So let's see first the case when you scale the random process. So let's replace x of t with some constant c times x of t. Then what happens to the power spectrum? It goes out, becoming magnitude square of c. So your power spectral density just scaled by magnitude square of c, the constant, right? Now, let's delay this one. You may take some t0, so you replace x of t with x of t minus t0. And as far as you have the integration interval covers entire line, you can see that the delay doesn't matter in the power spectral density, right? And what else? Can I claim that this equals greater than or equals 0 for all f? So the power spectral density is a real number, especially non-negative real number for all f. Yeah, see that? This is what? Non-negative real. And you take the expectation and take the limit. If this limit exists, the limit must be non-negative real. So power spectral density's definition says that power spectrum is non-negative real for all f if it exists. Got it? Sometimes textbooks define the power spectral density as the Fourier transform of a random process's autocorrelation function. That is very dangerous because using that, it's not easy to even prove this one, non-negativity of the power spectral density for all f. Got it? But using the definition, you can easily prove that. Now, here goes the Wiener-Khinchin theorem, extended version, because many textbooks just say that Wiener-Khinchin theorem is for a Y-sense stationary random process. So in order to find the power spectral density of a Y-sense stationary random process, you just Fourier transform autocorrelation function parameterized by delay tau as a paired parameter, the frequency f. But that is not the exact Wiener-Khinchin theorem. But anyway, let's see a generalized version. So here goes this magnitude squared. And be careful, whenever you have this times this conjugate, you have to use different integration variable. So even though this integration variable is t, you have t1 and t2. That's why you have t1, t2, and f. F is given, right? But integration variable must be chosen differently in two different integrations. So you have t1 and t2 and f, and naturally, this looks like what? Symplectic Fourier transform. But with f1 equals f2. Got it? So this is e to the j to pi f1 t1 minus f2 t2 with f1 equals f2. Got it? Anyway, and here the Gemini deviates, starts to deviate a little bit from ordinary derivation. And I love this Gemini's style. So far, it's the same. You just plug in what you have here. So you may drop this subscript t as far as you have the finite integration interval. That's why you have what? The ordinary autocorrelation function of random process x. And here you have symplectic Fourier transform, but with f1 equals f2. And you have integration intervals and normalization and limit. So by definition, excuse me, And here goes the trick. Let's define T as the average of this T1 and T2, arithmetic average, and tau then as a delay, time difference between T1 and T2, defined as T1 minus T2. Actually, you don't need to do that, but this is actually much better. Yeah. And you plug this in here to have the integrations with respect to T and tau. Got it? Then you have here something interesting. This one is expectation of T plus tau over 2, T of x of T plus tau over 2 and x of T minus tau over 2 conjugate. Right? Take half of tau and add them up. Then you have T1, right? And you take T minus half of tau, then you have T2. So this is exactly same as Rxx T plus tau over 2, comma, T minus tau over 2. And let's define this one as Rxx, unfortunately, tilde, which is does not mean complementary, but anyway, T, comma, tau. Now, this double integration has negative 2t to 2t as the integration interval for parameter tau. You can easily verify. And for the t parameter, you have the parameter defined this way. So it's like and given t, if I remember correctly, something like this. Yeah. Anyway, yeah. So here you have the. Just a second? Am I correct? Yeah, just a second. Yeah, so you have here what? Oh, sorry about that. So you change the order of these two integrations. Then what? You have the time average. Am I correct? Just a second. Something's not correct. Yeah. Just a second. Just a second. Okay. Okay, got it. Not this one. So here, this R tilde is defined as the time average of this function. And yeah, so this is a time average. So you take this one, and dt, and this one, and limit. Got it? So eventually you have the time averaged autocorrelation function with respect to tau Fourier transformed. That is the Wiener-Kinche theorem. Got it? Anyway, so even if your second order random process is not a Weiss station random process, first thing is that you introduce the average time t as t1 plus t2 divided by 2 and delay t1 minus t2, and then rewrite your autocorrelation function of t1 and t2 as a function of t and tau, and then you average with respect to t to have a function of tau. Then if you Fourier transform that one with respect to tau as a function of f, then you have the power spectral density. That is the Wiener-Khinchin theorem. And of course, if you have originally from the beginning, you have a Weiss stationary random process, then you immediately have the autocorrelation function as a function of tau. So you have the simplified result. The problem is that, so here, what happens when we have non-stationary random process that still gives you a well-defined power spectral density? And that is the origin of the problem is same as the energy spectral density of a deterministic signal. As you've seen, energy spectral density loses all the information of its Fourier transform of the deterministic signal because you just take the magnitude squared, no phase. And that phase information gives you some interesting part like this signal, that signal, having the same energy and same energy spectrum, just delayed version, but their energy concentration is different at time t. So this says that energy spectral density itself, that is the starting point of our definition of a power spectral density, loses information in time. So loss of time resolution occurs not only in the definition of energy spectral density and also power spectral density. Especially it's a non-stationary random process, then we have a serious problem. So we have no idea about the evolution of frequency content over time t. So at some time t1, we may have some high frequency signal and less low frequency signal. And t2, we have large low frequency signal and less high frequency signal. But overall, we have large low frequency and large high frequency signals. We don't know where they distribute in time. And you may say that that's why we have so-called short-time Fourier transform and similar definitions. So we take the window, time window, and then Fourier transform. Take the magnitude scale, like periodogram and something like that, right? And actually, there is another version we will see called the Wigner-Weil distribution, which is rarely taught in communications area, but taught many in image processing and wavelet related research. Anyway, we are going to talk about in that way, but before we doing that, let's see the important results about the Weiss stationarity. So whether you introduce this way or not, anyway, if we assume Weiss stationarity, we have just this is 1, so you have the ordinary result. Anyway, remember that the power spectral density of a general non-stationary random process may well defined for a specific random process, but we lose our time resolution completely. Then, what about bifrequency spectrum we've already defined? Does that also lose information? What do you think? And you already know that this bifrequency spectrum was defined as what? The 2D symplectic Fourier transform of the autocorrelation function, right? So as far as the invertibility is established, we do not lose information about at least autocorrelation function, right? So at least we keep the information about the autocorrelation function when we use bifrequency spectrum. Then let me ask you a question. What's the relation between the bifrequency spectrum and ordinary power spectrum over non-stationary random process? Probably you've already remember this way. So let's just use variable f1, then we have this relation. So given a non-stationary random process whose bifrequency spectrum is given by this capital S sub xx, f1 and f2, you can find the power spectral density by taking what? The height of the delta function along the line f1 equals f2. Got it? So the height of this impulse fence becomes the power spectral density. So do you see the difference? From bifrequency spectrum, you can recover all the information in the autocorrelation function. But you can't do that in general because you already lost other bifrequency spectrum information when you compute the power spectral density. Got it? So the section 1 of this document is all about this one. I just claimed. Okay, so you read it. And this bifrequency spectrum is also called as bispectrum, as I told you. And two-frequency spectrum, complex spectral density, generalized spectral density. But bifrequency spectrum or bispectrum may be a good name that contains most of the information. By the way, for Y-sense stationary random process, the bifrequency spectrum is given this way. So computing the bifrequency spectrum for any random process, and if you identify the bifrequency spectrum is in this form, then that is a Y-sense stationary random process. Right? And also, you have something interesting, which you already know. So if you have this input-output relation between two random processes x and y, then what do you have about the cross spectrum of x and y and bifrequency spectrum of y, something like that, in terms of the bifrequency spectrum of input and impulse response and something like that. And you already know that the cross correlation function between x and y is the autocorrelation function of x converged with h of t2 conjugate and our yx t1 and t2 equals h t1 converged with r xx t1 and t2. By the way, this convolution is with respect to the variable t2, and that convolution is with respect to the variable t1. And from these results, as you've seen in some graduate level probability and random processes textbook, you have in general the output autocorrelation function given in this way. Got it? And now we double Fourier transform the last line to obtain what? This way. Got it? So your output bifrequency spectrum is simply the Fourier transform of the impulse response as a function of f1 times the input bifrequency spectrum times impulse response, the Fourier transform of the system's impulse response as a function of f2 conjugate. And you have the similar results for the upper two equalities. Got it? So we have a very nice formula that relates the input and output bifrequency spectrum when we have LTI filtering. And you've seen in undergraduate and most of the graduate textbooks about random process, when we have a special case, input itself is wise and stationary. However, I'm not assuming that. This is the general result. And for the wise and stationary case, if you substitute this one here, then you will see that you have output existing only on the kind of main diagonal, which means that output is wise and stationary. And you can find the output power spectral density as you already know. So if wise and stationary, then this way, so you have am I right? Just yeah. Just comma. Yeah. Something like this. So you have the well-known result. Got it? By the way, again, we have abuse of notation here. This is the ordinary power spectral density with single variable. Got it? Yeah. Be careful. People use a lot of abused notations. The trouble is that, so far so good. The trouble is that if we want to extend to general linear filtering, not necessarily time invariant, then we have a serious problem. And from here, I just summarize the result. So you already know that input-output relation between two random processes after linear filtering is given by this form. Kind of extension of convolution integral. The problem is that now, if you want to find the output autocorrelation function, and then you want to find the bifrequency spectrum, you have a serious problem. So definition is simple, but you have some strange integration. Okay? Very complicated. So this does not work in general. Okay? So you don't have simple formula that relates the input-output bifrequency spectrum when you have linear filtering. Why is it so? Because general linear filter can be viewed as what? viewed as frequency shift filters, approximately. So you've seen that if the LTV filter is periodically time-varying filter, you've seen that output is what? Output is the input converted with LTI system plus input converted with another LTI system, then output modulated, summed, and another pass, LTI, modulated. That is actually can be written as input, LTI filtered, plus input modulated, LTI filtered added, input modulated, LTI filtered, something like that. So you can approximate, or you can find a very good approximation in general for linear filter, not necessarily periodical time varying. You may have these modulators. So the frequency components are quite convolved to generate specific frequency component. That's why general expression cannot be written in a very simple, intuitive form. Got it? So some result like this one, okay? This is a kind of desired result, right? See that? Output by frequency spectrum, input by frequency spectrum, and what is this? This is kind of transfer function, two variable transfer function of the linear time varying system, and that is also the two variable function. This does not hold in general. This requires very special structure of the linear time varying filter. So be careful. Okay? This is not in general. In general, you have this form. This is general. After you define this calligraphic letter H of F and tau filters. Something like that. So be careful. And then, since it's time's over, but we can extend our results for complementary bi-frequency spectrum, and you can do it yourself. By the way, the kind of homework which you don't need to submit is what? Try to prove the existence or not of the complementary autocorrelation function when you have the second orderedness of the random process, complex valued random process. Got it? Anyway, so we stopped here. And next time we are going to visit this mean square periodicity again because we still need to talk something about that. And then we are going back to the KL expansion. Last time I presented it to you for time-limited random process. And this is actually related to the time-limited random process that can be viewed as a Y-sense periodic random process after periodic extension. Last time I just said that given a time-limited random process, you can periodically extend it, and then you can apply KL expansion, but there was subtle something wrong last time. So I will talk about that this Wednesday. And then eventually I will talk about Wegener-Ville distribution. I'm not sure that this pronunciation is Ville. He's a French engineer, so probably Ville or something. Is it Wegener or Wegener? Probably in French it is called Wegener, and in German probably Wegener. I'm not sure. Anyway, so I will talk about something interesting that is directly related to what we've seen today. So we've seen something interesting, and you need to remember is that energy spectral density of a deterministic signal is what? Fourier transform of its time autocorrelation function with paired variable delay and frequency. Got it? And that will be used again and again. And some of you already know about some similar notion of ambiguity function. And some of my graduate students, I actually talked about it already probably a year ago. And we are going to review that again because eventually we will see something like, where is, yeah, quadratic time frequency analysis. That's all related to the power spectral density, Wigner-Weil distribution, and statistical ambiguity function, and autocorrelation function. Got it? Anyway, that's all for today.